Hello everyone, welcome back to Linked Frequency. In this tutorial, we are going to learn about triple voltage power supply design using EasyEDA. I'm Vaibhav Sugandhi, passionate PCB designer and startup founder in electronic industry. This is the third tutorial in practice projects for PCB Designer series. Let's get started with the design of triple voltage power supply design using EasyEDA tool. First thing first, in our product development cycle, we are going to start with the black box analysis. We have an input connector where we are going to connect the input source for the entire PCB, which is always greater than the 12 volt. Why? Because we are going to create a PCB for 12 volt regulation, 5 volt regulation and 3.3 volt regulation DC power supply. So at least our input voltage should be somewhere around 15 volt to 24 volt, which is industrial standard. To connect that particular power source to our PCB, we need an input connector. And then we need an input filter circuit to remove the unwanted noise or maybe a spike of impulses in the entire input section. So that's why we are going to add a 3 different input filter for 3 different power sources generated later on. Then we need a regulator section where we will be having a 12 volt regulator, 5 volt regulator and 3.3 volt regulator with a 1 ampere of a current rating for this entire power supply design. Thereafter, we need an output filter circuit as always for the linear voltage regulator to remove the impulses or noises or thermal imbalances created by a regulator circuit. That's why we will be adding the 3 output filters for 3 different regulators. Thereafter, each power supply or each regulator circuit will be having its own indicator to indicate that that particular circuit is working properly, and then it will be having its own connector so that we can access each and every individual regulator output separately independent of each other. This is how the entire black box analysis looks like for the triple voltage power supply design. I'm not going to dive deep into the details of datasheet analysis or anything that is already discussed in our previous tutorial. So let's jump into the morphological chart for the first component, that is all about 12 volt regulator. I have considered the same features to be compared in our morphological chart and with the almost same options that we discussed in our previous tutorial. First thing, we will be listing on all the feature detail about that particular component by referring its own data sheet. That's what we did in our previous tutorial, and that is what I did in this particular morphological chart as well. Thereafter, we will be filling the entire chart with the scores of individual features compared to each other. And then we will be adding all the score to get the ultimate score. As always, in this particular case as well, we got to know that the outperforming option in our entire morphological chart is LM7812 because our requirement is almost and exactly matches with the data sheet of LM7812. That's why it is scoring a 24, wherein the LM317 is 14 and BA1781 IC is 15 and Zener diode is obviously 17. Similarly, for the 5 volt regulator, we will be having the same features but the different options. First option, LM317 remains same as it is a variable voltage regulator. Second one is LM7805 and the third one is LD1117 and the fourth one is Zener diode. If I fill the entire morphological chart by studying the individual data sheet, we will be having this kind of a morphological chart in front of us. Thereafter, we will be giving a proper rating to each feature in comparison with the previous or the next one. And then we will be adding a score for all that particular feature for that particular option, and we will be ended up with the final score. If I compare all these 4 options, we will be having one option which is outperforming all the other 3. That is all about LM7805. This is how the morphological chart is very essential and useful for hardware design engineers. Similarly, for the third regulator, that is 3.3 volt regulation, we will be having a morphological chart. In this, we will be comparing the almost same options that we did for the previous tutorial and obviously the same features that we are discussing from last 2 tutorials. So if I do the same process for this one as well, like adding a score for each features, for each option, and comparing them with respect to the neighboring features and options. Then we will be ending up with the one option that is all about the first one, LM317. Now I think you might be a little confused. In our previous tutorial, we selected LM1117 3.3 volt because of its independent requirement, wherein in this case, we are selecting a LM317. Why? Because the input voltage is 7 volt to 40 volt, which is essential for us right now. Though we have a high dropout voltage, we need to have a very good margin of input voltage, wherein in our previous case, we have selected LM1117 because the input voltage is 12 volt. Right now, our input voltage is not 12 volt because it should be more than 12 volt so that we can generate a 12 volt regulations as well in the same input source. That's why we are going to go with the LM317 circuit. This is how the morphological chart is helpful for the converting of black box analysis into a white box analysis. And this is how the entire white box analysis looks like. We will be having a T-block connector with a 5 ampere of a current rating for the input voltage or input connector. And then we will be having a 100 microfarad capacitor with a 35 volt 3 times because each regulator will be requiring them independently. If I keep a one large capacitor input side, that is also a fine one. But at this point of time, I would like to go with a 3 different capacitor for each and every regulator separately. And then we will be having a first regulator as LM7812, second regulator as LM7805, and the third regulator as LM317 3.3 volt fixed voltage regulator. And then an output voltage or output capacitor's voltage will be different because of its output voltage from the linear voltage regulator. For LM7812, the double of 12 volt output, that is 24 volt, which is not available in the market. That's why we are going with a 25 volt output capacitor. And then 7805 will be having a 10 volt capacitor at the output side, but better to go with a little bit of extra feature that is all about 16 volt. And then we will be having a 6.6 volt capacitor requirement at the output of the 3.3 volt regulator, but we are going with a 10 volt because that is easily available and that is the only option after 6.6 volt requirement. Thereafter, we will be having a red LED for each and every regulator output and also a T-block connector, which is a terminal block connector for each and every regulator circuit. This is how the entire white box analysis looks like for the triple voltage power supply design. Now let's jump into the EasyEDA tool and start with designing our triple voltage power supply circuit. First thing first, I will go to the file, go to the new and create a project. Here I'll keep my repository as it is and I'll name it as a triple voltage power supply. Description, I'll give it as plus 12 volt, plus 5 volt and plus 3.3 volt DC power supply design. Oops, sorry, it's just a design, not designing. We have a habit of saying designing using EasyEDA, so that's why. So I'll click on a save and a new canvas will appear to me, and here I'm going to start with the designing activity as always. Now let's do it in a fast forward way. Alright, now you can see that this is how the schematic of triple voltage DC power supply looks like. We have connected the input connector to a VIN net label. This is called a power symbol or a power label in EasyEDA. We have a VCC and we have a plus 5 volt, and we can modify it as per our voltage level. So I have changed the name as VIN so that I can use this specific symbol everywhere so that we can connect the net from this particular input regulator or the regulator input to the point where the input is coming directly, instead of taking a wire and all, right? This is the professional way of connecting the one point to another point in schematic design. Similarly, I have used a V into the 3.3 volt regulator as well. And then we have calculated the different resistance value for each regulator. Because of change in voltage, the resistance value will decrease to maintain the specific current that we want on the LED side. This is the basic calculation which you can find in the basics of electronic course on our linked frequency. This is how the entire schematic diagram looks like. Now we'll jump into the PCB layout design and let's finish it as we always do. Alright, so this is how the entire PCB designing is all about. I have given a very good space for the entire PCB so that you can practice it at the beginner level, so that you will not get clumsy with respect to the placement of the component and dealing with the designators and all that thing. Okay, so I have placed the input connector at the middle of the entire PCB, and the entire PCB size will be 65 mm by 65 mm, and then we will be having a 3 input bulk capacitor and then 3 regulators. Of course, here you can notice I have not followed the IPC standard that I have spoken about in my previous tutorial. That is all about placing the component, that is heat radiating component, like a regulator on the border edge. I have placed this one at the border edge and these two exactly the symmetry of that particular placement, so that we can add the combined heat sink and we can add a cooling process for that. If you place any component in between these two heating elements, then it is a false IPC standard, or maybe not following a proper IPC standard. Of course, if it is possible, you have to place this regulator at the board edge and make it very proper. But at this point of time, as a beginner, you cannot do it that complicated circuit. That's why I have given an easy method to complete this project. However, after completing this project, give a try by yourself, placing this regulator on the board edge, this regulator also on the board edge, making the entire circuit in a simple way that is possible with respect to the IPC standard to be followed in the process. Again, using a single layer PCB, that is a challenging one, right? And thereafter, right now, I have not placed the regulator to the board edge, but instead I have placed them linearly and symmetrically, and have given a very good border here indicating it is a heat sink area. One thing that I have not done is designator organization or a designator arrangement. Let's do it in the live while I am talking. So here we have a C1 and U1 is at the best place. U2 is also at the best place. No worries to change about it. And here we have a C5. Let me change it to the top side. And then P1 is on the proper side. And then we will be having a C2. Let me change it to the top side. And then C4. All right, so then we have a C6. Thereafter, we will be having a R3. Let me place it somewhere here like this, probably. That is the best one. And LED 3 also. P4, I would like to place it somewhere here. And then LED 2 probably somewhere here only. Right, it is still visible. And then R2 is here. Or we can place a LED 2 somewhere here as well, but it will be not a good idea. So let's place it there only. And then we will be having a P3. Let me place it here. And then LED 1, R1, finally P2. Okay. So this is how the designator organization is all about. I have made it visible to one direction only. And this entire section or the entire heatsink area is indicated by a border as well as a heatsink area mark by a top silk layer. So you have to learn how to use these top silk layer and also very different tools or the options available in the entire EasyEDA, because you can see that there are a variety of tools available here. When to use them, how to use them is a tricky part, and as much as projects you complete, you will get to know about them in a different way. So this is how the entire circuit looks like. I'm going to look into the 2D diagram now, and of course you can see that all the nets are clear. So now I'll go to the 2D diagram. This is how the 2D diagram looks like, top side and the bottom side. Okay. And then we will be going into the 3D view. So this is how the 3D visualization is all about. Let me make it a green color PCB and background to be a black color. Of course, input capacitor and regulators are not visible to us. I don't know why, but let's ignore it for this particular moment. We can see that there is a connectors, input connector, output connector, and the entire PCB looks very professional for me at this point of time as a beginner level tutorial. So I don't mind changing anything at this point of time. So this is how the 3D diagram and the 2D diagram looks like. And thereafter, we will be having a file to export for the toner transfer method. I'll go to the PDF section, black on white, merged layer, all these things to be checked. And then we will be keeping a bottom layer alone, and then we will be unchecking other two, and the document layer is not necessary. So this is all about for PCB for toner transfer method. .pdf is an extension that has to be added. Thereafter, if I go to the desktop, you can see here, this is how the PCB looks like. Wonderful. Looks good for toner transfer method. I'll close it. Now we'll go back to our easy EDA tool. Here we'll go to the file again and export option. Then we will go for the maybe export BOM and no, why BOM is coming in the PCB layout, I guess. Okay, so there is a glitch in the software, I guess. Okay, so export BOM here, export option is here, and export PCB fabrication. Check for the DRC. There is no DRC error, so it will be generating a Gerber file, and I'll be saving this Gerber file on the desktop itself for zip.zip, right? Yeah, so Gerber file is also exported. Then going back to the schematic section, again going to the file section and export BOM. I think in PCB layout also we have option for export BOM. I don't know, maybe updated version of Easy EDA. So let's click on this and you get the BOM as well. So I'll add the power supply.csv. Okay, so this is a BOM and this is how the entire schematic looks like. So on desktop we have a Gerber file here, right? And then along with that we will be having our which circuit? This one, the BOM actually, right? So the BOM is also visible to us. This is how the BOM looks like. Of course, you have to make a lot of modification before sending this BOM for the vendor to get it supplied to you. But right now, I'm not going to focus on that. So this is how the BOM looks like, okay? So this is all about how to convert your, the triple voltage power supply design using Easy EDA. So we are converting a input voltage coming to the entire PCB into 3 different voltage as per the black box analysis. So here you can see that in our schematic or in our PCB layout, you have to connect a minimum of 24 volt to this particular input, or at least a 15 to 16 volt as per the 7805 minimum input voltage, which is plus 2 volt to the output voltage. Like 12 volt output means plus 2 is 14 volt. So 14 to 15 volt is a minimum voltage we should supply to this PCB, so that we'll get the 12 volt, 5 volt and 3.3 volt at the same time with a 1 ampere of a current rating. Of course, your input current should be more than 3 ampere, then only you will get the 1 ampere equally on the other side of the entire PCB. So that's why we added a very thick copper track here rather than adding a 1 mm track like output side what we added right now. So this is all about our triple voltage power supply design, guys. I hope you enjoyed the entire process of converting or creating a PCB with a 3 different power supply in a single PCB. I believe that you enjoyed and you learned something by doing it by yourself, okay? Thank you so much for watching this tutorial. I believe you learned something new in this, and see you again in the next tutorial with a very good project for your practice as a PCB designer, beginner in industry. So until then, consider subscribing to our channel Linked Frequency. Share this video and share about our linked frequency with your friends and fellow PCB designers so that they will get benefited as well. See you again in the next video. Until then, tune yourself to make a difference.